the number of ways one can choose k objects from a set of n distinguishable objects without bothering about the arrangement in which the objects appear is called the combinations of k out of n. So now you know permutations. And oh, you know combinations too. I guess your training in the principles of counting is complete. Now you can compute the probability of any event. Well, not quite. There are some special cases that you need to be aware of. You have seen how to choose k individuals from n people. That you can do in nck ways. There is an interesting mathematical formula where this expression comes from. If you remember your high school mathematics, you might remember that a plus b whole square equals a square plus 2ab plus b square. I could also write this as a plus b whole square equals 2c0 a square plus 2c1 ab plus 2c2 b square. Similarly, a plus b whole cube equals a cube plus 3a square b plus 3ab square plus b cube. I could rewrite this as 3c0 a cube plus 3c1 a square b plus 3c2 ab square plus 3c3 b cube. Notice that the denominator in the choose is the same as the exponent of b. If I keep going, a plus b to the power n equals nc0 a to the power n plus nc1 a to the power n minus 1 into b plus nc2 into a to the power n minus 2 into b square plus so on plus ncnb to the power n. So nck is the coefficient of the term a to the power n minus k into b to the power k. Actually, it is also the coefficient of a to the power k and b to the power n minus k. If you don't remember why, just remember your training on combinations. Now, what if you want to choose k groups such that each group has a different number of members, and by the end of it all the n people have been chosen. So let's say the first group has n1 members, second group has n2 members, and so on and so forth till the kth group has nk members. But the condition is n1 plus n2 plus n3 plus so on plus nk equals n. So in how many ways can you do this? This can be done in n factorial divided by n1 factorial times n2 factorial plus so on nk factorial ways. A mathematician will tell you that this is the formula for the multinomial coefficient. That is, if you consider the expansion of a1 plus a2 plus a3 plus so on ak to the power n, the coefficients of the terms can be found using this formula. For example, how many ways can you arrange the letters in the word Mississippi? Well, there are 11 letters in which M appears once, P appears twice, I and S appear 4 times each. You can consider each unique letter as a group. So the answer to the question is 11 factorial divided by 1 factorial into 2 factorial into 4 factorial whole square. Let's solve a probability problem. Suppose there are 9 people boarding an elevator in a building with 12 floors. What is the probability that on each of 3 of the floors, 1 person disembarks, and in each of other 3 floors, 2 people disembark, and nobody disembarks on the remaining 6? First of all, there are 12 to the power 9 ways in which 9 people can disembark on 12 floors. This is the total possible outcomes in the sample space. Now, in how many ways can we divide 9 people into 3 groups of singletons and 3 groups of pairs? Using what we have just learned, we can do that in 9 factorial divided by 1 factorial into 1 factorial into 1 factorial into 2 factorial into 2 factorial into 2 factorial ways. Then we need to divide the 12 floors into 3 groups. One group of 3 floors where only one person disembarks, another group of 3 floors where 2 people disembark, and another group of 6. This can be done in 12 factorial by 3 factorial into 3 factorial into 6 factorial ways. So we can compute the probability of our event as 9 factorial by 1 factorial cube into 2 factorial cube into 12 factorial by 3 factorial square into 6 factorial divided by 12 to the power 9. Phew, that was quite a handful, wasn't it? Well, these kind of problems are called combinatorial problems, and they can be quite complicated. Even seasoned experts and mathematicians can struggle while solving them sometimes. So don't be disheartened if you find them difficult. Just understand the basic principles. There is one more special case. Consider the problem of putting k balls into n slots. You have seen that you can do this in npk ways. But suppose you are now allowed to put more than one ball in a particular cell. This problem can be asked to you in a different way. So far, we have considered that all the objects are distinguishable. But now, what if the objects were identical? This is just another way of saying that you are allowed to put more than one object in the same slot. Let us see if we can understand the problem visually. I'm going to draw n cells. Each line represents a cell wall. So there are n plus 1 such lines. I'm going to represent the balls with a circle. Now I'm allowed to put as many circles between two lines as I want, as long as the total circles don't exceed k. So one possible configuration is shown here. Consider the above diagram as a sequence of lines and circles, and the length of the sequence is n plus 1 plus k. Now notice the first and the last place are fixed. I can't have circles in those places because these are the walls of the first and the last cells. In between, I have a sequence of n plus 1 plus k minus 2 or n plus k minus 1. I just need to put k circles anywhere in the sequence. That is, I need to choose k positions from the n plus k minus 1 positions. From our knowledge of combinations, we know that this can be done in n plus k minus 1 choose k ways. And that's the answer to our question. I just wanted you to be aware of these special cases. Any good student of probability should be able to tackle these problems when presented to them. Alright, that concludes your training in combinatorics. We have climbed another hill, but the saga of climbing the data science mountain continues. Want to continue the journey? Then subscribe and like. If you want to survive this harsh world, you must learn the probability laws.